Mr. Hefner here. Here's a video on the universal electric force. Okay, Coulomb's law. So the opposite charges attract and similar charges repel. Similar to gravity, the force decreases with the inverse square of the distance. So French physicist Charles Augustin de Coulomb published the laws in 1785, which started research in electromagnetism. So here's gravity's formula, pretty straightforward. Universal gravity is negative gmm over r squared. So you got two masses, the big mass, the little mass, and the distance between them r. And there's an action-reaction pair of gravity. And the constant for g is 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. For the electric force, you see it looks very similar. So we got a constant, k, which is Coulomb's constant. 9 times 10 to the 9 Newton meter squared per Coulomb squared. Instead of having two masses, we have two charges, Q and Q, or some will do M1, M2. In that case, you can go Q1, Q2. But I like using big Q and little q. Okay, you got the distance between them, which is also squared. So it's almost the same thing. So it's pretty easy to do. So as you notice, though, if you take a look at the constants, if you compare K, which is 9 billion, to G, which is a hundredth of a billionth, there's a huge difference. K is about 135 million trillion times larger, or 1.35 times 10 to the 20. So it doesn't take a lot of charge to get a comparable amount of force compared to gravity. In fact, gravity is hardly noticeable until you are planetary sized, but you can notice electric forces quite quickly. So here we have a 400,000 volt Van de Graaff generator with a radius of 12.5 centimeters, and it's providing negative 70 microcoulombs of charge. Find the instantaneous acceleration on a positive 2e alpha particle, which is made of 2 protons and 2 neutrons at a distance of 5 meters. So here's our alpha particle. Alpha particles are just helium nucleus. So that's 2 protons and 2 neutrons. So it's an atomic mass of 4 and the atomic number and number of protons of 2. So what we're going to find out is the acceleration at this distance. So we're going to use the new formula. F equals k QQ over r squared. So we got k is 9 billion. The charge, negative 70 microcoulombs. That's negative 70 times 10 to the negative 6. 2 elementary charges. Positive 2 times 1.6 times 10 to the negative 19 divided by 5 meters squared. And so we get the alpha particle experience 8.064 times 10 to the negative 15 newtons of force, attractive force. So I should have a minus sign right there. So what's the acceleration? So the force is 8.064 times 10 to the negative 15 newtons. I should throw a minus sign in front of that. We got 4 atomic mass units. So an atomic mass unit is basically close to the mass of a proton, 1.67 times 10 to the negative 27 kilograms. Okay, so we'll do 4 times that. And we'll divide that over under the 8.064, and we get the acceleration, 1.207 times 10 to the 12 meters per second squared. Divide that by 9.8, and it gets you 123 billion G's of acceleration. Quite a lot. Alright, so we'll do another one here. So a 50 kilogram person stands on the surface of the Earth. The person has around 2 times 10 to the 25 protons in their feet near the ground. That's just an estimate, I'm not really sure. And the ground has an equal number of protons as well. So together the protons provide the normal force. So the normal force really is just electric repulsion. Okay, so since the electrons can move around but the protons can't, we'll just stick with the protons. Find the distance between the person and the Earth. So you're actually levitating on the Earth when you stand on it. But how far apart are you, right? So using universal gravity, 6.67 times 10 to the negative 11. Mass of the Earth, 5.98 times 10 to the 24 times the 50 kilos for the person. Divided by the radius of the Earth, 6.38 times 10 to the 6 meters squared. Get negative 489.95 newtons, or 109.9898 pounds. Or we could have just used the simple formula because it's the surface of the Earth, F equals mg. That's 50 kilos times 9.8 newtons per kilo. That's 490 newtons, or 110 pounds. So yeah, the simple formula makes more sense in this case. So here we go. You stand here on the Earth, gravity pulls you down, the normal force keeps you from falling through the Earth. And if you zoom in, same thing. So now we want to find out, hey, if we know the amount of force that the electric force has to provide to keep you from falling through the ground, then how far are you from the ground? So we got 490 newtons. We got 9 times 10 to the 9 for our K value. We got 2 times 10 to the 25 protons, plus another 2 times 10 to the 25 protons, each with an elementary charge each. Okay, so all together, we're going to get 9 times 10 to the 9 times 2 times 10 to the 25 times 1.6 times 10 to the negative 19. But we have 2 of these, so we're going to square that. And dividing into the 490 newtons, and we get 5.32 times 10 to the negative 21 meters. And I think that's not even the width of an atom, so you're pretty much right in there. Yeah. So that's 5.32 billionths of a trillionths of a meter between your feet and the ground. So I had to estimate the protons. If you click on this link, JLab, you'll see where I got the number of protons from. I don't know. It'd be hard to count for real, right? So, yeah. So in summary, the universal electric force, Coulomb's laws, very similar to gravitational force, Newton's laws. So it's pretty easy. If for gravity, it's just gmm over r squared, or gm1m2 over r squared. For the electric force, it's kqq over r squared, or kq1 and k2 over r squared. Biggest differences being g is pretty weak, 6.67 times 10 to the negative 11. But K is 9 times 10 to the 9, or 9 billion, pretty strong. So you got your 2 masses. They have an action-reaction pair of forces from a certain distance apart. And you got your 2 charges, which have an action-reaction pair of forces. And they're a certain distance apart. But usually the big object like the Van der Graaf or the planet doesn't really move. Maybe vibrate a tiny amount, but it's hard to tell. What we're more worried about is what the small mass with the small charge does. Okay, I hope this helps. So don't forget, forces always exist in pairs, according to Newton's third law. All action forces must have a reaction force. Oh, and here's a picture of Coulomb right there. I hope this helps. Thank you.